Hi guys, today's screencast is on nuclear power, our fifth and final non-renewable energy resource. Um, we're going to examine the advantages and disadvantages. Like any energy resource, there are pros and cons. But before we do that, I think it's important that we develop an understanding of how a nuclear fission reactor actually works, and then we'll look at it in a larger context of the nuclear fuel cycle. America's history with nuclear power, it's a fascinating story, and sort of one that can be described as a sort of a love-hate relationship, I suppose. In the 1950s, many analysts suggested that nuclear power was going to be the future, and they projected that by the year 2000, over 21% of the world's energy would come from nuclear. That did not happen. We know that. Currently, the world's energy, if you subdivided it, only 6% of it comes from nuclear power. So obviously, something went wrong. And yeah, you could certainly point to many events. Um, One event in particular, 1986, the Chernobyl accident, right? So a total nuclear meltdown that certainly changed the public's perception of nuclear power overnight and instilled a bit of fear. Also, of course, all of this was happening simultaneous to the Cold War and fears of nuclear war and the proliferation of nuclear weapons. Finally, environmentalists were also very concerned about nuclear power because, as an energy resource, we know it produces a lot of waste and high level radioactive waste that could be dangerous to the environment and to human health. So, all of those reasons really slowed it down, and as a result, it's currently the slowest growing energy resource in the marketplace today. But what's really interesting is that those same environmentalists who villainized the nuclear industry are actually calling for its revival because they're pointing to the atmospheric issues that we have with fossil fuels, right? Greenhouse gases contributing to global climate change. Well, when you look at nuclear power and you compare it to coal, nuclear releases one-sixth the amount of carbon dioxide than coal. So some say, hey, it could be a good solution to climate change. It doesn't release suspended particulate matter, which is really harmful to the human respiratory system. And also, it doesn't give off any sulfur dioxide, which is a precursor to acid rain. So, nuclear, many are arguing now, might be a solution to many of our environmental problems. So we'll look at that and let's give it a fair shake and see if it is a solution. First of all, let's explore how nuclear actually works. As a process, it seems very complicated because it is very complicated, but the task, the premise behind it is very simple. It's designed to boil water, right? Simple as that, right? You boil water because you want to produce steam. That steam creates kinetic energy. That kinetic energy then spins turbines to create mechanical energy. That mechanical energy then gets transformed into electrical energy, which is sent out through the grid. But how it heats that water is a bit more complicated, right? And it's done through a chain reaction process that we call nuclear fission, where we use radioactive isotopes. And those radioactive isotopes specific to the nuclear industry are from uranium 235. All right, that's going to be the focus of the nuclear radioactive isotope fuel that we're going to talk about. Uranium 235 is fissile, meaning it's fissionable. In other words, a neutron bombards the nucleus of the uranium 235 atom to split it. And as it splits it, it actually releases additional neutrons from the original atom. And those neutrons get expelled at an amazing velocity. And since they have such great velocity, they have amazing kinetic energy. And that kinetic energy gets transformed into thermal energy, producing an enormous amount of heat. And that's what we're looking for here. But it also, not only that, those neutrons continue, right? And they find and seek out other radioactive isotopes of uranium 235 in which they fission those nuclei of uranium 235. And then this process is ongoing and it continues and it sustains itself. The concern is, though, of course, is that it can overheat, right? Obviously, the goal is to produce heat, but you don't want to produce too much heat to cause a catastrophic meltdown. So oftentimes they use water as a moderator, and that water actually slows down this process a little bit and helps to sustain it. And by slowing down the neutrons, it increases the probability that they'll continue the chain reaction sustainably while producing an enormous amount of heat. Now, the fuel, uranium 235, is extracted from the Earth, and uranium 235 is then compressed into a fuel pellet, and that fuel pellet is packs a punch, to say the least. It has an amazing energy density, right? Because in this little pellet, about the size of a cigarette butt, there's equivalent energy here on the order of about 1 ton of coal. So that's a lot of energy, and so all of those pellets are then packed into a fuel rod, right? So you have hundreds and hundreds of these pellets packed into one fuel rod, and those fuel rods, which are sort of hollowed out tubes, are then assembled in a massive fuel assembly that are placed in the reactor core, which serves as the site of nuclear fission. So there's about 50,000 of these fuel rods placed into the core itself, and let's take a look at that site. Now here is the diagram of the nuclear power plant. You guys have one in your notes, so take a careful look at that. Get to know it well. You should become old friends with it. You'll notice that there are letters on your nuclear power plant diagram, and those letters are keyed out below, and they identify the structural components of the nuclear power plant. And then they are defined in terms of their function. So it's going to be really important that you guys can key out each of those parts and explain what they do. Okay, so let's go through this together here. We'll start with the letter A in your diagram. That's where the magic happens, right? So this is the core itself. This is where the fuel assembly goes, where those fuel pellets and fuel rods are stored. And this is where nuclear fission takes place. Okay. Now, in order to control the rates of reaction here, they use what we call control rods, and these are like neutron poison because what they do is they help to slow the reaction down. And they do that by using specialized material like cadmium and boron that are capable of absorbing those neutrons. And so when they want to slow it down, they inject the control rods between the fuel rods themselves and slow down the reactions. If they want to speed up the reactions to increase their rates, they actually just pull them right out. And in this way, they have a handle on how quickly these chain reactions take place, and they can control the temperatures. What else they use to control the temperatures? Of course, water, right? And so you'll notice that this whole plant is situated on a river or a lake. And so most nuclear power plants are found on a body of water where they will take up some water, and the water is pumped into and around the core to keep it cool. And not only is it keeping it cool, but it's also going to be producing steam. So the amount of heat that's created also gets expelled because that heat is essential in producing steam. That steam has kinetic energy. That kinetic energy spins the massive turbines to produce mechanical energy. That mechanical energy then gets converted to electrical energy via the generator, and the electrical energy is then transmitted through the grid to supply the electrical demands of the surrounding community. Now you're going to notice that all of this, produces a lot of waste heat, right? In fact, the whole process is very inefficient. In accordance to the second law of thermodynamics, 75% of the energy is lost as heat from a nuclear power plant. That means only 25% of it, up to 30%, is actually useful. So, more often than not, the waste is discarded, and it's discarded directly out back into that water source, that lake, river, or ocean, where it can contribute to significant thermal pollution. Right? You're warming the water up, you're reducing dissolved oxygen, and ultimately that's going to affect aquatic life. What you'll notice in your diagram, take a look, letter F, that is a coolant tower. So some nuclear power plants have these massive towers that instead of releasing the waste heat into aquatic systems, release it to the atmosphere as steam. Other features you guys should be made aware of is the containment shell. This is a massive galvanized concrete structure that's galvanized with reinforced steel that can be several meters thick, and it's designed to prevent radiation from leaking into the environment, as well as preventing external threats from exploding the nuclear core reactor, right? So the threat of terrorism is obviously a real threat, and so we want to prevent this from catastrophic failure. They've actually built them to withstand massive hurricanes, tornadoes, and even the impact of a 747 jet. Pretty incredible stuff. So a naturally occurring or a well-run nuclear power plant, there's going to be minimal, if no, radiation waste whatsoever. There's no carbon dioxide being given off from this process. There's no atmospheric pollutants. It's a fairly clean system. The only pollution that's usually associated with a well-run nuclear power plant is, of course, thermal pollution. All right, so we were just talking about the useful energy, as we said, about 25 to 30% efficient. However, let me suggest to you that is just the sort of the tip of the iceberg here, because there is a whole fuel cycle that also demands energy, and ultimately it reduces the net energy yield of nuclear power significantly. So let's take a look at that. Alright, so this is the nuclear fuel cycle. So as we've just described, the reactor site where nuclear power is taking place is about 25% efficient. So what that means is that 75% of the energy coming from nuclear is lost in accordance to the second law of thermodynamics with energy transformations. So that's 75%, but there's more to it because first of all, we have to extract the uranium oxide from Earth's crust. We have to mine it, usually through open pits. And so doing this requires energy. Not only that, we take that uranium fuel and we have to enrich it. Right? Naturally occurring uranium has both uranium-238 at a very high percentage and the fissile uranium-235. Well, you need to bump up the percentage of uranium-235 to roughly about 3 to 5% in concentration in order to use it as a fuel pellet. So they have to fabricate those fuel assemblies and enrich the uranium. And doing that requires energy. So mining and enrichment in fuel fabrication requires an additional 9% of the total usable energy. So already we're at 84% of the energy coming from nuclear is lost to the reactor site and to the enrichment, fabrication, and mining of uranium. That's not it though, because a lot of that waste material that's left over, that radioactive decay and the spent nuclear fuel rods and so forth, all have to be taken care of and stored. And so all of that requires additional energy on the order of about 8%. So already, now you add up 9%, 75%, 8%, we're already to 92% of the usable energy is lost. But that is not it, because it keeps going. Each of these reactor sites here have to be decommissioned. They have a shelf life, right? Too much radioactive material accumulates, they become unstable and very unsafe. And so what they have to do is they have to dismantle them. That requires more energy. Not to mention all of the fuel assemblies and the waste has to be stored for a minimum of several thousand years. That requires even more energy. So when we're through with it all, more often than not, the energy that's produced from nuclear is exceeded by the amount of energy that is used to produce it. And so what this can yield is a negative net energy yield. And so that is one major disadvantage of nuclear power. We're going to stop right there, and our next screencast, you guys are going to examine the ecological consequences of nuclear power.